All right, I'd like to walk through number 15, free body diagram and 2D rigid body supports, just to kind of wrap things up here, and maybe it will help someone else. I'm not sure. Anyways, our first problem, we're given this beam, and we have a pin at point A, and we have a roller at point B, and then we're given this force along the top. Part A says, identify the support reactions on the beam shown in figure 1. A is pin and B is a roller. And it says to check all the possible support reactions on the beam, even if some of them are equal due to the due to the loading given. Make sure the reactions in the set you choose do not depend on each other. So the first thing, and obviously you can see these here, but I'd like to go and explain it a little bit. Let's talk about point A first. So we have a pin here, right? And we're trying to figure out what movement pin A prevents this thing from doing. So obviously, if we try and twist it to the left or the right, it can move. So we're not going to actually be limiting the moment around point A. So this is going to be unchecked. We already have that. And then if we try and pull it up or pull it to the side, it's not going to move. So that means that we have a reaction force on A in the x direction and A in the y direction. Cool, so we've eliminated all three of these so far. Next, let's take a look at Bx. And so we know that this is a roller, right? And so if you were to try and roll this, assuming this doesn't exist, it would roll in the x direction, right? So there's no reaction force right there. So we can eliminate that option. By, now you try and push down on that roller, right? It's not going anywhere. That's because you have a reaction force pointing up, right? So we are going to check that. And finally, we have the option for moment at B. And it looks like here they have an applied moment, and due to the roller being here, the roller is not going to actually stop any moment from happening if you forget about everything going on in point A, right? So that we don't have any reaction force for the moment at B. So we've kind of eliminated all of our list here. Part B is just drawing the free body diagrams for that. So just like I was saying, AY, AX, BY are the three that we selected up here, and those are put on this chart. Part C was identify the support reactions on figure 2. Okay, so let's start off with point A, right? We have the same thing, we have a pin, and so this is going to limit us. We try and pull it up, not going to go. So we already know that AY is selected, try and pull it to the right or the left, can't go. So AY and AX, perfect, we got those. All right, so NA represents the normal force of A, right? And in this case, we don't have normal force, and that's because this is a pin and it's already limiting in the X and the Y. I'll show you an example of a normal force here in a second, but that's not something that we're going to have. Moment around point A, remember, try and turn it around. That's you can turn it all you want, so you cannot select moment around point A. There's no reaction force. All right, BX. This is a rocker on B now. It's no longer a pin. Sometimes hard to conceptualize, but that's all right. So BX, right, you have a rocker. If you try and push it to the right, it'll still go, right? And that's because your rocker, it's not actually holding it down, it's just pushing up against something. So you can't select BX, nor can you select BY for the same reason, because if you try and pull it up, it's going to go, right? There's nothing holding it back. Now, if you look at it, the rocker is pushing down at this angle, and it's on a plane or a 30-degree slope. And so that'll kind of tell you, okay, rocker, it's not gonna hold it in the X and the Y like a pin might, but the whole beam is being supported by it. So where's that force going? And that's due to the normal force on B. The normal force is the force that points perpendicular to the plane that it's on, and so in this case, the normal force would point from this plane, this 30-degree angle, all the way up and complete that. And then the moment around B, it's a rocker. It has the ability to move like that, and so there's nothing preventing it from doing so. Part D shows you kind of what I'm talking about, AX and AY on this side, because it's the pin. It's not going to move to the right, nor is it going to move up. But at point B, you have that normal force, right? Nothing is preventing it moving this way in the X direction or the Y direction. But it is preventing it from going down into that surface, and so that force is pointing perpendicular from that 30-degree slope, right? And just make sure when you do your normal vectors to have your normal always perpendicular to that surface. It'll mark it incorrect otherwise. For problem 2, we were given this funky little pipe thing, and it says identify the support reactions on the rod supported by a smooth surface at B and a collar at A, right? Okay, so going back to A, right? You isolate A. You don't think about anything else. You try and pull it up, it's going to go up. So you can't select, there's no reaction force from A in the X direction, and the Y direction. Do the same thing for the X direction or the Y direction. You can move it. So both of these are going to be unchecked because there's no force holding it back, right? If you just don't think about anything going on over here and you're just thinking about this, you try and slide it to the right, it'll move to the right. It's not holding it in place, and it'll move up. Then you think about kind of what we were talking about before. What is holding it up? Because obviously it's not moving anywhere. And that would be due to the normal force at A, right? So same thing that we said. It's very similar to a rocker in this sense, where this force is just pointing straight. It's perpendicular to this little pipe thing that it's supported on, right? And also, now that we're here, looking at moment around A, if you're to try and turn this around this point, that's not going to happen. It's conceptual I think it's pretty conceptual here. I don't have really another way to explain it in a better sense, but I selected moment around A. There is a reaction force, so you can't twist around that thing. All right, B, remember this is a smooth surface. Remember, smooth surface. So if you try and move it to the right or the left, you can move it, right? No support, no reaction forces. Same thing with the Y. Pick it up, it will move, right? But there is still a force that is preventing it from just going through this thing, right? And that's going to be that normal force, which is perpendicular to the surface, right? Moment around B, try and turn it around that point, it'll turn. There's nothing holding it back. And then for that free body diagram, this actually took me a minute because I couldn't figure out how to make this little moment icon appear. So the normal force, once again, is perpendicular to that surface there. And then this moment around point A is kind of given by this blue arrow here. I had to double click that if you're having a hard time doing that. And then at B, remember we don't have anything X or Y, but we do have that normal force keeping it from going to the surface, and that's pointing perpendicular. Part C is identify the support reactions on the disk shown. Okay, this one's a little funky, and quite frankly, it's just strange. Check all the possible support reactions on the disk. Okay, so we're thinking about the disk, right? We're not thinking about the spring, we're not thinking about up here. We are literally just thinking about this disk. If I take the disk and I want to move it left, right? Something is preventing me from moving it left. Great, okay, so we can say that there is a reaction force in the X direction. That's our first option, so we'll click that. AY, is there anything preventing me from moving it up or down? No, there isn't. So we're going to leave that one unchecked. Now we're asked moment around point A. This is a smooth, I believe it says, it should say that it's a smooth surface. There's nothing that's connecting it. So if I wanted to rotate it, theoretically, there's nothing stopping me leaving this unchecked. At the point O, X and Y, right? If I want to pull O down, I can pull O down. And if I want to pull O to the right, I can pull O to the right. And you're asking, well, it's staying in one place, right? There has to be something. And OX and OY are actually taken care of by the force of the spring. there's an example in class where you just, instead of drawing the x and the y, if you have like a beam that goes down from something or supports it underneath, then you just draw the vector of the beam. And so we can think of the spring as just a force that goes up this way that keeps it in place. Pretty simple. And then moment around B, I don't even know where B is, to be honest, so I did not click that, and that was right. Same thing here. You have the weight force going down. You have AX, right, the support or the reaction force from this thing going into the wall. It's pushing back out. And then in place to keep that point O in one spot, you have force, or this spring force, right? And that takes care of OX and OY. Cool. All right, next one, and I'll move to the iPad. Great. All right, we're back on the iPad, and we are given this diagram, right? It says, determine the horizontal and vertical components of reaction on the pin A and the reaction on the beams at C. Okay, so we have, let me just move my little highlighter thing here. C, we want the vertical component of the reaction at pin A. So over here we want whatever that reaction is or whatnot, and it looks like because this is pushing down, this is going to be, and so it's pushing down here to prevent that from rotating. That's not super important. Okay, and it says for part A, determine the horizontal component of the reaction at the pin A. Okay, so if we're looking for the horizontal component at A, we're looking for this, and we're figuring out what force is keeping it in place, right? And it looks like this whole thing is being kept in place by this force, AX, right? Otherwise it just goes somewhere else, I guess. And the way that I went about solving this, first of all, is I figured out, so this is kind of like a systems of equation problem, right? You have these unknowns and you need to solve for a known. What I did right off the bat is I know that we can solve for the moment around point A, right? And the moment of A can be modeled off of this equation. And in this equation, we have the force of C times 1.5. This gives us our moment around point A due to C in the y direction, right? Minus 4,000 newtons, which is our given, going down at point B, and then you multiply that by the total length to get your moment from that force, right? In doing so, what we did here is we essentially made an equation where one of our variables can transfer over into the individual forces, right? And giving this, this whole equation, we can solve this out for FC, right? FC shows up in both the moment and the horizontal and vertical component forces, right? So we took 11.3 thousand newtons, and we set up our system of equations for the horizontal and the vertical components, right? So the horizontal components, we have the sum of all forces in the x direction is equal to 0. And this is because this is statics. Everything is equal to 0, right? And we know that there's only one force pointing left or horizontally and one force pointing right, which is great because now we have a given. We know FC, and we can solve for AX, right? And so what we're going to do for that first equation is AX. We move this over, right? You take AX and you move it to the other side. You get AX is equal to FC cosine 45. And this red here is just simply taking what I found FC to be without rounding the number. So I hope that's clear. In doing so, you can find AX, which is the horizontal component, right? That gives us negative 8,000 newtons. So that's going to be the answer for 1, at least with these numbers, negative 8,000 newtons, excuse me. And then for AY, we kind of do the same thing, right? We know that AY, there is this force, and this force, right? And we know this force, and we know FC. So all we have to do is solve for AY. So it's pretty similar to the last one. We take our system of equations, the sum of all forces in the y direction equals to 0. That is positive AY plus FC sine 45 minus 4,000 newtons. Great. Now let's take that and we'll replace FC with the value that we found earlier. So we have AY is equal to negative, and I'm not sure if I said that, but I moved this over. AY is equal to negative FC, which is given by this expression, sine 45, because we're finding it in the y direction, plus 4,000 newtons, right? Because AY turned negative, I multiplied out that negative through everything. So it's plus 4,000 newtons. And that would give you the answer of negative 4,000 newtons. So kind of to recap, sorry that was a little unclear because I forgot I multiplied out that negative all over here. Rearranged this expression, the sum of all forces in the y, negative AY is equal to FC sine 45 minus 4,000. That's a little bit more clear because you have a positive FC sine 45 and you have a negative 4,000. Flip that sign on the AY because you have AY negative out here and you want to make that positive. So you're going to flip it, you get AY and you get negative this, positive that, negative 4,000 newtons. And there should be a unit on that. Newtons, perfect. And then we're asked to find the magnitude of force on reaction at point C, on beam at point C. Okay, well, we already did that, and I just proved it by saying this is our magnitude. It's everything that we have, our F and our X and our Y. This was a little stupid. I don't think I really needed to do that. We already found it up here. This is the total magnitude of FC. And that will plug into part B of the Mastering Engineering. Cool. Last problem we have here is problem number 5.15, and we're given this whole thing. We have this like beam looking thing, and we have this distributed load on the top. We have a triangle distributed load, and all of these. We have an applied moment. Looks pretty bad, not gonna lie. It says, suppose that W is equal to 0.8 thousand newtons per meter. That's just our distributed load value, and then our force applied is 4.5 thousand newtons. For part A, it asks, determine the horizontal and vertical components of reaction at A. Okay, so we're looking at Fx and Fy over here. So like our force X, A, and our force Y, A. And that should be the other way, force Y, A. Right, we're looking for that. Okay, cool. Well, the first thing that we do when we see something like this distributed load is we're going to want to find the centroid of where that distributed load is applied, which is basically the center of which all of that load concentrates down onto in terms of solving the problem. So we can break this up. We have a rectangle on the left, and to find the total force on this whole area, right, we're going to take this value, which is how many newtons per meter is applied, represented by these arrows, and we're going to multiply that by the total length. It's just like finding the area, right? So 6 times 0.8, and I have that force rectangle is 6 times 0.8. That equals 4.8 thousand newtons. And then if you recall, finding the centroid of a rectangle is pretty easy. You just chop it in half, and it will be right in the center. And so the center of 6 is going to be 3. So you have your X centroid, and you have your total force applied over that distributed load. For the force of the triangle, we're going to do the same thing. We're going to look at it, we're going to be like, okay, we need to find the area of this in terms of W. So we have 3 meters, and we have 0.8 thousand newtons per meter. Multiply those together, but then you're like, oh wait, it's a triangle, and so you have to multiply that by 1/2, right? That will give you 1.2 thousand newtons, and then to find the centroid of that triangle, if you recall, the centroid of a triangle is going to be 1/3 of it as long as this side is bigger. So it's like if you have a triangle like this, it would be 2/3 because that's the most mass. 1/3 in our case is true because the most mass lies to the left. So it's like 1/3 of the triangle there. Anyways, we multiply the distance. So this is for the centroid, right? We have 6, which is our total distance here. We have to add this because it is calculated around A at least, right? Or the moment, if you were to find the moment, because the centroid is just the centroid of the triangle. And then to calculate the centroid of the triangle, we're just going to have 1/3 of that distance. So 1/3 of 3, 1/3 times 3 is going to equal to 1 meter, right? Okay, cool. So now that we have our centroids of our rectangles, our triangles and our rectangles, we can calculate the total downward force. So the reason that we're going about calculating the total downward force on this object is that we don't have any other force to calculate, right? So when it asks us to determine the horizontal and vertical components of reaction at A, right, we don't have any other components besides our downward force. And so our vertical component of that downward force at A is going to be the force that this distributed load gives us plus the force that this distributed load gives us plus the force that we already have, right? And so sum of all forces in the y direction is equal to 0. Statics is equal to AY, which is AY right there, minus R, which is given by R is, in this case, is equal to our resultant of distributed loads, right? So that's going to be these guys, and F is given to us by this force that's been applied, is equal to 0. I don't know why I put equal to 0 again. Anyways, move that AY to the other side, flip the sign on it, right? Flip the sign on everything, and you're given AY is equal to R plus F. Okay, so to calculate R in this case, R is just the forces that are due to the distributed loads. You have to remember that, well, actually, you don't even have to use moments for this because it's literally just every force that's pointing downward. So you have your force from the triangle, right? That's going to be your 1.2 thousand newtons, which is right there, and then your force from the rectangle, which is 4.8 thousand newtons. Add those together, you're going to get 6,000 newtons, and you have 6,000 newtons plus your 4.5 that's applied at the very end. That's going to give you 10.5 thousand newtons, and that's your total force in the y direction. So pretty easy, 10.5 thousand newtons. And then you're asked to find the moment at A, and so now you kind of have to think about, okay, so the moment at A, when it asks for moment, you're thinking about all of the forces and their distance away from that point, right? So the triangle, we'll start with the triangle, right? The triangle here, you want to calculate its moment. You know its centroid is at 1 meter, right? And we're going to use that centroid to find the total moment around point A that all of this distributed load causes, right? And knowing where that force is applied, you can kind of just simplify, you can simplify the thing down, right? So if you have your like, say you have your rectangle here, and you have your triangle here, and you found the centroid of it, now you can just simplify it down to like a force vector, right? So this is your force triangle, and then this is your force force rectangle, remember it's just in the center. Force triangle is going to be, what did we say that was? 1.2 equals 1.2 thousand newtons, and this is 4.8 thousand newtons. And then we're also given, don't forget about the applied 5 kN, or 5,000 newton per meter, this way, right? And then it's pretty simple if you remember how to calculate moments, which I'm sure you do. You take your force, so 4.8, you multiply it by the distance it is away from the place that you want to find the moment. In this case, we're given, it's going to be half of 6. Oh, where did that go? Half of 6, which is going to be 3. 4.8 times 3 plus 1.2. And how far is it away? Well, it's 1 meter here, right? But you can't forget about all this, and so it's going to be 6 plus 1, which is going to be 7, right? And then you're looking at this applied moment, and if you recall, a clockwise moment is going to be or a positive moment is going to be counterclockwise, and this is opposite, so this is negative. So you're just going to subtract, what is it, 5,000 newtons minus 5 kN. If you do the math, you are going to get 68.3 thousand newtons in this case, and that is just your moment from your rectangle and your moment from your triangle plus your applied moment. It's just going to equal that. Pretty simple, but it could be a little tricky. Yep, and that's it.